Morning, everyone. Thank you very much for inviting me to present one of the topics. As already, I guess, Neeraj Sinha sir has mentioned that now we'll be actually looking into the prospects, even in conventional seismic, which we have been looking and in deep offshore, and there are certain challenges which we now have to address, uh, which is now actually to meet the growing demands in our country. Uh, the topic which I'm going to show is related to identification of thin beds, which would not have been possible, uh, I guess, in past 20 or 10 years. But with the development of new technologies, we have a lot, I'll say, or ample amount of technology by which we can identify those thin beds. But still, the technology which I am going to present today is relatively new and a unique technique, which is actually devised by Professor John Castagna, a well-known name in the industry. So this is actually about one of the techniques which we call as phase decomposition. It is, I'd like to emphasize it is not instantaneous phase, it is not spectral decomposition which we do, because spectral decomposition is like uh, creation of, or basically decomposing your traces into sinusoids of frequency. Here, we are actually decomposing any seismic trace into a waveform of different phases. And this is mathematically very, very much possible. Now, the the foundation of this theory, I'll say, lies pretty much when we do the analysis in terms of fluid substitution for any gas bearing, or I'll say any brine bearing sandstone. So we know that if we replace that brine in the sand with gas, then we can clearly see the change in the phase. And now, when we are actually talking about the thin means seismically thin, which cannot be resolved, means it is further beyond the concept of lambda by 4, which we use for resolution here. Okay? So this is what I was saying. If you see this case, we say that on the left-hand side of this one, we see there is a seismic trace which is actually reconstructed from phase gathers, which actually contains different phase components. And as I said, it is not like instantaneous phase, because instantaneous phase do not contains any information about the amplitude. But this phase gather, which is constituted of different phase components, contains here the phased information, which we can see here at the bottom, minus 180 to plus 180, and the relative amplitude for those phases. Now, if you see the figure on the right hand side and the middle figure, which is basically our response for a very thin layer, which if it contains a brine, this is what we are getting. Again, I'm saying thin means it is not resolvable from seismic. And when we substitute that brine with gas, then the thing which we can expect is a dim spot. And there is a reduction in my amplitude contrast, I can say, or I'll say the impedance. And this is what will happen when we take the 90-degree phase component, or I'll say minus 90 degrees, specifically in case of a bright spot or a dim spot. So minus 90-degree phase component corresponds to the hydrocarbon effect. Now, having said that, it's not always that hydrocarbon will only show that minus 90-degree phase component represent. Anything which is subtle and it's below seismic resolution will have a 90-degree phase component. But the anomaly which we see here in the amplitude will be larger if the hydrocarbon is present in that thin layer. It can be low saturation gas, it can be very thin layer, but it will impose itself on this 90-degree phase component, be it plus or minus 90 degree, also where plus 90 degree is evident. It will impose itself as a 90-degree phase component in case of thin layer. And further, the anomaly in terms of the amplitude will be enhanced when it is hydrocarbon filled. This is one of the synthetic example. If I can illustrate it here, like consider an example where there is a top shale and a base shale, and there is a very thin uh, interbedded channel, and there is an interchannel area. If you see here, the demarcation of area is given like the channel fill actually is further lower in terms of the impedance from the laterally interchannel area which is present in the in the in the vicinity of uh, top shale and the base shale. Now, if you see on the normal seismic, because if you see here, I'm so sorry, it's not working. So, if you see here on the reflectivity on the right hand side of figure A, then we don't see much difference in the reflectivity coefficient which is coming from the top and the base shale. And this subtle change in the impedance cannot be captured in the normal seismic. Now, when we decompose that with the 90-degree phase component, clearly we can see in the channel fill we have a very sharp amplitude change in the minus 90-degree phase component, although that 90-degree phase component is present in the interchannel area as well, but the anomaly in terms of the amplitude change is not that large. So it will always pose itself as an anti-symmetrical wavelet phase whenever this kind of feature is present. Now, to show the value, we'll have to actually present certain case studies, definitely. Now, sorry, this is one of the case study which actually is done by Professor Castagna along with the clients in Gulf of Mexico. And again, if I see here on the left-hand side, there is a normal seismic, and there's a inline which is actually shown at the bottom at the location of the dashed line over the image, or I'll say the map, which is actually an attribute. And they have drilled it at the location as it is shown with the red well, or at the top it's a red symbol. Now they have drilled it. Again, this is for a bright spot scenario. They have drilled it, although which is different from a bright spot because it is peak over a trough. Although we know in bright spot we have normally trough over a peak. But probably they have drilled it because of the scenario they have in their mind, that it is actually having a good trapping stuff. And on the basis of that, they actually have extracted the amplitude, or I'll say the RMS or maybe the maximum amplitude map for that particular reflector. And now they have the anomalies of the amplitude all over the area. And on the basis of that, they were planning to drill another well, which is shown here with the symbol B. Now, there was a notion whether all this red or even the further brighter yellow is a good prospect. But later on, after certain analysis, they discarded that no, B is not that much prolific. Now, to substantiate that, they further did this phase decomposition. And now if you see, when they did the phase decomposition and when we see the 90-degree phase component, it shows that, okay, there is a trough over a peak at the location where it was drilled, and it is actually agreeing. But when it comes to that location which was planned, we see the lateral movement, it's further towards the southwest, and it's not present in that map. So this is how actually the phase decomposition is helping. And further, one may argue that if only on the basis of phase decomposition I cannot do the identification of hydrocarbons in the thin bed, definitely. But whenever we are doing the phase decomposition, it further helps us to actually carry out certain other techniques, like even if you want to carry out AVO, now we have an area where we can directly focus to do the AVO. Rather than just looking everywhere to do the AVO, now we have focused area, we can actually then go for AVO or any other techniques to further substantiate that, okay, the the anomaly is because of hydrocarbon. This is another case study from offshore Brazil, where if you see, this is very good instantaneous amplitude map over the formation which was targeted. And the area which is actually circled here, or in the oval shape, are those areas which were dry. But if you see, we cannot decipher anything from this instantaneous amplitude. But now when we do the phase component analysis, the 90-degree, or I'll say minus 90-degree phase component clearly shows that these areas where actually they have got the success after drilling the well are present in minus 90-degree phase component. And the area which were dry well, it goes off and it is present in even component, which is 0-degree phase. Okay? This again is another case study from Gulf of Mexico. And if you see here, this is actually bounded by faults. And this is the maximum amplitude or maximum negative amplitude over the area on the input data. And now if you see, there was a well drilled which is star marked here, and now they have a good elongation in northeast southwest direction, and now they were thinking to drill a well in the northwest direction, but it turned out to be a dry well. The reason is, later on after the studies, and the RE suggested there was a pressure barrier. Because of that, later on they actually put a fault, and when this phase decomposition method was implemented, they found that the area which went dry is actually falling under the even component. The odd component is showing that the prolific area is only towards the south of west. In case of carbonate, we have studies in US Permian Basin, US Basin of Permian Formation, and then we have case studies from Sichuan Basin, China, where this method has been employed, but has been implemented, but not directly for hydrocarbon, but rather for the identification of those areas where we can have good porosity because of the alteration of carbonate. This is a specific case of dolomite, where if they see initially on the first graph, we don't have any correlation between the amplitude and the porosity. But when we took the plus 90-degree phase component here, which is the odd component in case of carbonate, because unlike sand, we mostly have minus 90-degree phase component, be it dim spot, or bright spot, or even we can say complex reflectivity coefficient in case of plastics or loose sediments. But when we go to carbonate, this turns out to be plus 90-degree phase component, which is again the odd part. But here we can clearly see that there is a correlation between the porosity and the amplitude, which is also correct, because if we see that the amplitude is basically decreasing and my porosity is increasing. So in summarization, I can say that we have a tool which is actually devised, and I think this tool may be present with our parallel, you can say, companies as well. Now this is technique which we use in DSG Lumina, and Professor Castagna himself is actually working on this technology since years, and it was actually first published and later on patented by Castagna in 2016 and later onwards. And there are so many theories and so many papers on this phase decomposition. And with this tool, which is now commercially available, now we can do this analysis for identification of thin bed, and if there is a presence of hydrocarbon in those thin bed, we can analyze it further. Again, as I said, this can be again utilized in combination with AVO for the spectral decomposition, because in order to be in a particular frequency band, we need to do the spectral decomposition. Either it can be continuous wavelet transform or maybe CLSSA. So all those things can be combined along with the phase decomposition. Recently, we have been working on some of the projects in ONGC. We are awaited with the results, and in first look, the results are encouraging. Although we are doing it on onshore data, if the results are encouraging, we'll go for the offshore area. Okay. That's all from my side. Finally, I'd like to thank ENP Conclave Organizing Committee for allowing me to talk on this topic. And I can see the faces under whom I have grown and still growing, like be it Chandrasekharan sir or Srivastav sir or Pinagdar sir. So I'm still in the phase of growing, but I'd like to thank them also because throughout my career they have been there, be it any projects, they have been guiding me. And especially to Professor John Castagna, Carlos Moreno, and Gabriel Gil, because they have shared me, and I've been working with them since last 6 months on some of the projects, and they have been sharing these information, these papers to me. And finally to Samir, who is my country manager of Landmark. Thank you.